This is chapter 6. So chapter 6 is kind of nice because it's only 6.1, and it's not too long, but it is quite complicated. And there's lots of different versions of it. So I guess the thing is to learn the basic principles, and then you just have to practice applying it in different contexts. But most of the time, the questions are not too tricky. Again, it's the idea of the batteries where they kind of just have a lot of information, and you just need to pick out like this bit and this bit and this bit tells me what I need to know, and the rest is not very relevant. So let's get started. Okay, next slide. Again, so this is all stuff we've gone through in class, so hopefully it's not that exciting. So in fuel cells, it's spontaneous, which is the same idea as a galvanic cell. It's chemical to electrical, so they produce energy. You still have an anode and a cathode and electrolyte. And remember that an electrolyte is something that is a liquid that can conduct electricity, so charged particles, whether electrons or anions and cations. But it's different from primary and secondary cells because you've got to have a continuous supply. So that's probably the biggest part. It's got to be continuous. And it's very efficient. So fuel cells are much more efficient at producing electricity than petrol or than other green sources of energy. But as we'll find out later, they don't actually produce that much. So in fuel cells, the oxygen is the oxidant, which means that it is itself reduced. So we again think about those words. Oxidant, it causes oxidation. It itself is reduced. So hopefully that's something we can remember. And then the reductant is the fuel, which is often hydrogen, but it can be a carbon-based stuff as well. So you can see that you've got your oxygen gas coming in. That's your oxidant, meaning it's reduction. So that's going to go in over here. That, again, an oil rig cat. That's happening at the cathode, which is positively charged. You've got your hydrogen gas or your fuel, which comes in, and that's happening at the negative, which is the anode. So that's going to be oxidation. The fuel moves over the anode and is converted into ions and electrons. The electrons move through the external wire, which is like around here, to the cathode. Ions are consumed at one electrode, migrate across the solution to the other. The cell produces about 1 volt, and the byproducts are water and heat. So you stack them for more voltage. So you actually get like a stack of them. That's why they can sometimes take up a lot of space. They're used in like aircrafts and that kind of thing, also in batteries for laptops. And the byproducts are actually water and heat, so stuff in the middle. So you can also have alkaline as well as acidic. So alkaline is a fancy word that means basic. So if you think about stuff like oven cleaner or when you have an upset stomach and you take like an antacid or that kind of thing, that's basic, that's alkaline. Whereas acidic is something that's acid, so vinegar or hydrochloric acid, things like that. So acidic is when it's got H plus, and alkaline is OH minus. Okay, and we can use them in either. So you've got the overall reaction is the exact same thing. This is one that we did in class, and we had to look up all of the parts of the data booklet and try to figure out what we would actually use. So I won't go through all of it now, but I will quickly show you guys, I guess, some of the basic working, which is on this page. So it's much more environment friendly. So we always check whether it's alkaline or acidic. The overall reaction is always the same. And these half equations are in the data booklet. So yeah, so it looks like that, which you should have in your notes. And you can see that you've got your H2 and your OH minus goes to 2H2O. And again, your oxygen and your water produces OH minus. So again, it's all about that OH minus. Again, in this one, it's relatively simple. You've got your hydrogen as a fuel and oxygen as a fuel. It's in an acidic environment, so you've got to think about your H pluses. And I'll see if I can quickly bring up the data booklet, which you would think I would have a downloaded copy, but let's find out. There you go. This is probably, it looks like it's from 2017, so it's probably not the updated version, but it's probably got what we need for the, nope, it's not helpful. I will quickly Google it. Okay. Anyway, so that's that one. Making hydrogen fuel cells. So hydrogen fuel cells seem to have zero emission, but they can actually also produce a lot of greenhouse gases. So often the hydrogen is from fossil fuels called steam reforming. Then you've got a bunch of different things here. So you've got methanol plus water, with a catalyst of nickel produces CO2 and hydrogen, and then obviously that carbon monoxide can produce carbon dioxide as it reacts with water. So yeah, producing the hydrogen that you need can actually produce a lot of other things, which is not so good. So obviously, if we're using hydrogen fuel cells, you can see that you've got wind, solar, etc., hydroelectricity, and then you've got our fuel cell unit over here. So you've got, like I said, domestic appliances, laptops, and automobiles. There's a bunch of different things. So yeah, basically, potentially it has a lot of capacity to change the way we do electricity, but it just depends on how we, I guess, do that. So storing hydrogen is quite tricky because obviously it's going to explode if it's exposed to flame. So you can transporting it can be quite dodgy. It's a gas at room temperatures, and it's just a bit dodgy. Obviously, it burns and it disperses quickly, so perhaps it's safer than petrol, but unknown. There's a bunch of other fuel cells. So fuel cells that use carbon, such as methane or propane, the electrolyte will usually be acidic, and in this example, what you have to do is you have your fuel, and you know that it's going to produce CO2, and then all you do is use cohees. So this is one of my favorite parts of chapter 6 because it always makes sense, and I think it's really good practice from chapter 4 and chapter 5. So then you have your fuel, in this case methane, which I'll talk you through in a second, and then CO2, and all you do is key elements, oxygen add water, hydrogen add H+, electron states, and you'll definitely make sure it's balanced. And it says, although CO2 is emitted, this is better as a fuel source because it's still really good at converting energy. So we'll quickly have a look for our data booklet so I can show you what we're doing. But also in the meantime, here we go. Just ignore my housemates having loudness in the background. So reduction is always going to be O2, goes that way. So that's good to know, I guess. And you've got your methane. So you've got methane here, goes to CO2. So we do our key element. We know that our carbon is balanced on both sides. Next is oxygen. So we have 2 oxygens over here. So we add 2 H2O. Now on this side we have 4 hydrogens here and another 4 here. So it's 8 in total. So I haven't balanced this correctly, so that's always a bit awkward, isn't it? But you get the gist. So that pretend that one is an 8, because I'm dumb. And then you'd add 8 electrons. Okay? So that would be what you would do. And this one is straight from the data booklet, which we'll have a look at in a second. So in our data booklet, I really should save this to my file, shouldn't I? We went through and looked for all the different ones containing water. So this one contains water, but unfortunately it is got the peroxide, so we don't count it. We've got our O2 plus H plus goes to H2O, so that one's the one that we just used in our previous example. And we know we can use that in acidic environments because it contains the H plus. You've got another one that contains peroxide, so we don't use that. And you've got your H plus goes to H2 gas, so we're allowed to use that in acidic environments. You've got water goes to alkaline environments. So again, we've got to think, is it H plus, is it OH minus? And there should be another one, unless I'm really dumb. Oh, and I forgot about this one, sorry. And O2 plus water goes to for OH minus. So you've got 2 for H plus, 2 for OH minus. So that's how you figure out those and that. This one goes through all the different types. And the point is you don't need to memorize it. You just have to memorize some of the basic ideas. So it's exactly the same as other things. But in this case, you've got alkaline and methanol. And it just depends on to whether you've got the OH minus or, OH minus, or you've got H plus. So in the majority of the rest of the examples, they're all H plus, but sometimes there will be an alkaline. So again, it's just practice, practice, practice. But you don't need to memorize them. You just need to remember how you do it. So pretty much H2 is going to be the thing that is reacting. Oxygen is always the oxidant. And then you just have to know if it's alkaline, you follow the Cohees rule. When you have your fuel goes to CO2, and if it's alkaline, then you need to find the stuff from the data booklet that involves your OH minus. So question 46, this is one that we did in class, and I quite like it, but it is a little bit tricky. So I'm going to show you guys with my prepared one. Sorry, just trying to find it. Here we go. Okay. So hopefully you can read that. Obviously it's C because I've already circled it, but let's talk through. So you can see that a fuel cell is currently under development for blah, 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 blah. So it tells us there's a reaction of methanol and oxygen using an acidic electrolyte. So because of the word acidic, we know that we can use H+, and it's methanol and it's oxygen. Okay, the reductant in the cell reaction and the half reaction of the anode. So the problem is we know oxygen is the oxidant. So straight away, the reductant in the cell reaction, so the reductant, is definitely going to be uh, methanol, because we already know oxygen is the oxidant. That's why it happens. So it's not B and it's not D. That's why I've crossed those ones out straight away. And then the half reaction at the anode. So the anode is where an oil rig cat. So anode and oil, right? So its oxidation is loss. So A is losing electrons. Nope, it's actually gaining. And C is gaining electrons. So it's actually losing. So therefore it has to be C, because you know oxygen is the oxidant. The reductant has to be methanol. And it's at the anode. Anode is oil rig cap. So you're losing electrons. So without doing any of the actual maths, that's the answer. But if we were actually going to do it, um, yeah, you'd see that you'd start with CH3OH, goes to CO2. Again, key elements, carbon, carbon are balanced. You think about your oxygens, you've got two, so you should have one H2O over here because you've already got an oxygen over here. Then you count up your hydrogens, so you've got 1, 2, 3, 4, 5, 6. Therefore, you have 6 H plus, and then you have 6 electrons left over, and then you insert states. Done. Okay, so hopefully that makes a little bit of sense. So disadvantages and advantages, not too complicated. So it's nice because, let's just make sure, yep. Fuel cells, so disadvantages, basically they need to be constantly supplied. It's a continuous supply, so obviously that you have to figure out a way to do that. It's expensive, it's not widely available, and your electrodes have to be really specific. They have to be conductors, they have to conduct electricity, they have to be catalysts, they have to force the reaction to go quicker, and they have to be able to keep everything apart but allow them to be in contact. So it's a very specific setup, which you'll see in the pictures in other slides. The advantages is obviously there's no CO2 released when hydrogen is a fuel, so that's really helpful. They're very efficient and they don't need to be recharged, but again, they don't need to be recharged because it's a constant supply. So it's kind of a double-edged sword. So fuel power stations are 80% efficient, so that's super awesome, whereas coal are only 30 to 40. Again, it's converting chemical to direct, lead to electrical, so like the galvanic cells we've been looking at. Whereas coal, it's a long process. So you got chemical goes to heat energy, then the heat energy is used to like turn turbines, which is mechanical, which then goes to electricity. So because every time you change energy, you lose basically you lose things as heat. So the reason that coal is 30 to 40% efficient is because it changes 4 times instead of just going straight from chemical to electrical. Again, it's a slow rate of reaction, so like lots of bad things, whereas coal is cheap. And then again, lots of really good things. It's quiet, it's clean, it's the future, whereas this is loud, noisy, and pollution and bad, but it's what we tend to invest in because we're silly. And then again, this just goes into primary, secondary versus fuel cells. So hopefully we are well aware of this by now. So primary cells is something that cannot be recharged, like galvanic cells, depending on the specific context. Secondary cells are ones that can be recharged, so they go from the galvanic cells where it's chemical to electrical, and then electrolytic, or when it's backwards, so you go from electrical to chemical when they recharge. And then fuel cells when they need to have a constant supply. And it just does the same thing. So it tells you that, and that's the end of the slideshow. So thanks everyone.